Um, Let me share my screen so you can see the slides for this talk. There we go. So as you can see, this is going to be about studying computer science at Cambridge. And there are four things I'd like to take you through. Very briefly, why would you want to study computer science in the first place? What would you be going on to in your career? What kinds of skill are you looking to build? Perhaps how is it different from engineering or mathematics? If you're interested in computer science, then why would you choose the University of Cambridge to do it? And if you're coming to Cambridge, why would you choose Homerton to do it? And once we've got through that, I'll look at how we actually apply. So there'll be some information coming up about the TMUA test, how you apply for that, what that's looking for. And also I'll show you a sample interview question. So you get to see the other part of the process as well. So let's get started. Why computer science? Well, first of all, the reason I did computer science was because I loved it. I was a programmer when I was your age. I loved writing software, and I was slightly interested in hardware. But for me, it was all about what we could do with it. What were the new possibilities, the new technologies, the fact that it's always changing. It was fast paced, and it is certainly an exciting career and industry to be in. When I was at Cambridge, I began to realize that the reason I liked it so much is because it's creative. You really do have to make new stuff. You're not just putting numbers into the same old equations that every other physicist can do. You're not just reacting bottles of chemicals together just like any other chemist can do. You're actually writing new programs that solve problems that other people have never solved before. That's clearly creative. It's very fun. And it makes you employable. It clearly makes you employable as a software engineer. It will make you employable as a software development manager, but also in the transferable skills. In and around computer science, there's an awful lot of stuff going on. Radio engineering for wireless networks, Bluetooth, embedded systems engineering, robotics, patent law. Who'd have thought that's part of computer science? Even becoming a lawyer, getting into ethics. How do social media applications change the way society works? Are there ethical things that we should do? Are there unethical things we should avoid? With a good computer science background, you can really understand what the technology is making possible, and how that's likely to change society, how it's already changed society. And of course, you might well be interested in computer science because you think it's the future. It probably is. So yes, really, why not study computer science? So why do it at Cambridge? Why would you want to sit in this particular lecture theatre? In fact, this is lecture theatre 1 in our William Gates building, the computer laboratory at Cambridge. And at the front we have, that's Richard Mortier. Richard is a contemporary of mine. He's a computer scientist himself, and he's busily lecturing there about operating systems to one of our first year groups. So why do this at Cambridge? Well, actually, a lot of computer science was invented in Cambridge. We do a lot of work in CPU architectures, and over the years, that's meant everything from actually building the very simplest processors that just made it work, not optimized, not fast, not low power, just work at all. That was 1960s, 1970s technology. And we've been leading the world in CPU architectures ever since. A lot of work was done on what's called self-timed logic. That was pioneered in Cambridge, in Manchester as well. And that looked at how we can build computers that don't need a clock. You've maybe never thought about the clock, the clock frequency of your CPU, and you maybe think that bigger numbers mean it's a better computer. Not really. Bigger numbers means it consumes more energy. So what we'd really like is a computer with the slowest possible clock you could get, and there's nothing slower than 0. So that would be the ideal energy efficient CPU. We did a lot of work on that in Cambridge. Computer networking. There were lots of networks all around the world, but in Cambridge, we came up with some really pioneering technologies that were simultaneously cheap and gave quality of service. Quality of service means that you can get guaranteed audio and video transmission speeds. So your video call, your telephone call won't break up. And that's not just probably, but that's actually guaranteed. So we did a lot of work on that in Cambridge. We in computer science, you call this dog fooding. What does that mean? It means we built our own computer network that we ran around Cambridge. We connected the colleges together. We connected the departments together. We built it with our own hardware, and we tried it out. We collected data. We improved on those designs. So a lot of that work was done in Cambridge. Computer graphics, similarly, we've done quite a lot of work there. Computer graphics, I'm sure you'll have, if I say graphics, you conjure up some idea of what I'm talking about. Most people think it's about graphics output, displaying things on the screen, perhaps 3D goggles, virtual reality, augmented reality. It certainly is all that, but it's also information capture. It's a webcam, it's multiple webcams, it's actually positioning sensors and building the computer's model of the world based on what's actually in the real world. That's used in the special effects industry for the movies. And of course, it's used in surgery these days. So surgeons can perform an operation from the other side of the world by performing an operation on a plastic dummy in front of them, but every hand movement is being sent across the internet and then replicated by a very precise robot at the other end that's performing surgery on the real patient. So we still do a lot of work in computer graphics. Believe it or not, what did we invent in the software world? We actually invented the subroutine in Cambridge, where when I was a student, the lecture theatre where I was taught computer science, if you looked out of the window, you could actually see what's called Wheeler Street. And Wheeler was named after the gentleman who invented the subroutine. That's what function calls are based on. And of course, all of modern programming is based on function calls. So that all comes out of Cambridge as well. We've got a long history in cybersecurity as well. And in what we call formal semantics, proofs of correctness. These are probably things you haven't come across much in your academic careers so far. But this is something that's really of interest to industry. And what you would say is, look at the medical profession. Look at how professional they are at what they do. Why is it when you go to your doctor, you really trust them? The advice they give you is correct. If they prescribe some drugs that help you get better, you actually do get better. They don't make your disease worse or kill you. They're really good at what they do. Look at the computer industry. Well, software crashes all the time. Companies get hacked all the time. This isn't really very good, is it? We're not comparable in that level of professionalism. And what we're lacking is formal proofs of correctness. And we do a lot of work on this in Cambridge. We don't want to test our software. Testing is a waste of time. You might not find the problem even if it's there. And it takes ages to do. It's very expensive in industry. What we'd like to do is a formal proof of correctness that says, not only do I think my hardware works and I can't find any problems, but I've actually mathematically proved that it does work. And not only do I think my operating system works and is not hackable, but I've proved that fact. And my application software and all the libraries it uses and everything around that. So we can get a fully complete, formally proved system. Industry is already adopting this. There's quite a lot of the big companies are doing proofs of correctness for their big software products that are hosted in the cloud. And it's part of the reason why you don't hear about them being hacked very much, but you do still hear about small and medium-sized companies being hacked. That the technology hasn't propagated through the industry yet. It's only the really big, really strong technical organizations hiring graduates, of course, from places like Cambridge that have got the brain power to do that sort of technology. We also do quite a lot of software engineering practice. And one field in particular is the economics of security. So if you're running a company and you maybe sell your products online, obviously lots of people do these days, you think, well, how much is it going to cost to make my system secure or even do a proof of its correctness? And what's insurance going to cost me? Oh, well, insurance is cheaper. So let's not prove it correct. Let's run the risk of getting hacked. One day every few years, I probably will get hacked, but that's okay because the insurance is cheaper. You know, that's a slightly broken way of thinking, but it is the way industry works at the moment. So how do we move on from that to that more professional approach, as you find in airline pilots, the legal profession, the medical profession, from my earlier example? So we're doing huge amounts of work here in computer science, and I'm sure many of the things, these examples, are things you wouldn't even think of. It's probably not what you think of as computer science, but computer science, computer technology really does encompass all this stuff. We've got to get it all right, and we're doing all of this in Cambridge. A few years ago, we surveyed our incoming first year, and we asked them, what do you see yourself doing after you graduate? And about 75, 80% of them said, I'd like to be a software engineer and I see myself working at Google. And that's a perfectly good thing to say. But when people actually graduated, that same year group, only about 5% of people went to work for Google as a software engineer. Other people went into CPU design, networks. They stayed on in academia doing research. They became theoreticians. They became economists in the security field, did PhDs in that area. People went in to invent new programming languages. They huge fan out as you realize the full breadth of what computer science is about. And you'll find that you get really interested in particular parts of it. And so it's really important to be studying a degree, as we do with the computer science tripos at Cambridge, that is so broad and gives you all those opportunities. The other points I've got on the slide here really speak for themselves. Cambridge computer science is a very competitive subject. So if you do apply and you are successful and you do get in, you really will be working with the best people in the world on computer science problems. And that's a huge networking opportunity. You really are learning with the best people. After you graduate, whether you work in the same company or you split up, 2, 3, 5 years later, you'll bump into each other. And you'll start to have some exciting ideas, and that's where the startup culture comes from. We're quite close to London. We have a huge startup culture in Cambridge itself. We call it the Cambridge ecosystem, Silicon Fen. The Computer Lab Ring is our alumni association of all the graduates who have started their own companies. So there are lots of reasons to study computer science at Cambridge. What we're going to try to do with our Cambridge computer scientists is not teach them about the technology of the day. So we're not going to teach you how to write Java programs, Python programs. We're not going to teach you JavaScript, TypeScript, React, Angular, Node.js. We're not going to teach you how to make mobile phone applications either. All of that is because it's a complete waste of our time. If you wanted to learn those things, with a Cambridge degree, you can spend an afternoon and get a textbook. The textbook will cost you 20 quid, the afternoon of your time, probably a good investment if you want to get into this, and you can just pick up those things. So what we are going to teach you in the academic environment of the computer science tripos is the mindset. We're going to teach you about the big problems in computer science. Like, why are subroutines so important? Why has that completely revolutionized the way we do computer programming? What are the equivalent concepts in hardware, in theory, in computer networking? And so in the next 5, 10, 50 years of your career after you graduate, when you hear a news article on the radio, or you read a news article and somebody says, hey, I've invented a problem, a solution to this problem, you'll think, oh, wow, I know how significant that is. That's something I really need to jump on. I need to reorganize my entire company to embrace this new technology. Or you can say, yeah, that's just noise. People have had that same idea in the 60s, the 70s, the 80s, the 90s, and the noughties, and it never works. So If you think you've solved it, that's great, but I'm going to give you a couple of years to prove it. I'll bet you go bankrupt. And with that, that real deep appreciation of computer science, you can come to those value judgments and with very good certainty be correct about what you decide. So we're really interested in what are the big problems in computer science, where are the open research problems, where are the next big developments going to come from. And all of that is rooted in the depth that you really can't say, is quantum computing going to be the next big thing? You've absolutely no idea. If you guessed, it would be nothing more than a guess. What you really need to understand is, what's the problem with classical computers? How do they work? Why can't we make them go faster? In fact, we already use quantum effects in modern CPUs. We have done actually for about a decade. But how have we done that? In what way has that use been limited? What's the breakthrough that's needed to move us to the next stage? Same with satellite communications. We've had satellite comms for quite a long time, but we don't yet. You don't have a satellite in space. I don't have my own satellite in space. Maybe in 20 years' time, we'll all have our satellites in space. How would that change the world? What would it take to make it happen? So what we're trying to get across is through the real depth, the detail, the real technical nuances of the computer science subject, understand what are these really big problems. And I've said this on the last line, our goal is to transform ordinary people who are interested in computer science and don't really know what that means, but are willing to come to Cambridge, be a blank canvas, let the computer science tripos write on you, teach you what computer science is about, show you the really big problems, and let you appreciate those for yourself. And then you get really passionate about some of these problems. You take them on board, you make them part of your career, and you either solve them, that would be great, or you take some steps towards it and make a contribution back to the field that allows other people to work with you, and together you can solve the problem. So that's the overview. The detail about how the course is structured. I'll skim through this because a lot of this information is on the college website and the Computer Lab website as well. We're divided into 3 years. The first year, part 1A, is getting you used to Cambridge, getting you used to the system, understanding what a lecture is, understanding what a supervision is, and that means how to make them work for you. It's actually quite hard to make a lecture work for you. If you sit down and watch the TV news, that's quite easy to absorb. And if I let you do that, then asked you some questions about what's going on in the world, you'd have understood enough from the news to be able to talk back to me. But if I talk to you for an hour about something detailed about the internals of CPUs and transistors and electronics and stuff, and then try and get you to talk back to me, you'd very quickly find that all the detail had become a jumble and you didn't quite get how it was all supposed to work. So understanding how to use lectures and absorb the content takes quite a while. So part of that's in the first year. Supervisions help with that. They give you some worksheets to work on, some problems to think about, and there are practical labs as well. You can see here the huge breadth of courses that we teach in the first year. Some stuff that you'd expect to have. Foundations of Computer Science is a programming course. Object-oriented programming is a completely different style of programming. Algorithms is the classic deterministic algorithms, things like Dijkstra's algorithm that you may have heard of. We've got a bunch of stuff that falls under databases, computer graphics, digital electronics, but the kinds of material that you'll come across there is probably not what you first think of when you hear that there are courses with those titles. So, for example, databases will teach you about classic relational databases from the 1970s, SQL. It's a really important technology. It's one of the only technologies in computer science that's been around since the 1970s and is still here. Right? The 1970s, count it up, that's 55 years ago. That's a long time. how many other bits of computer science are still there 55 years later? It's doing something right, but what exactly? So understanding that, understanding its limitations, looking at other systems, graph databases, real-time event streaming, document databases, comparing and contrasting all of those, being able to do the kinds of real-time analytics. That's really important. That's another part of databases these days. Computer graphics, of course, we have to draw on 2D surfaces. These days, we draw on 3D surfaces. If you've seen the kind of New Year's party, you shine a data projector at the side of a building and try and put a picture on the front of a building. Front of a building's not flat. If you want to make your picture look correct, when this building has got pillars and window frames sticking out forwards and backwards, you've got to do some really clever distortion effects in the image that you project, so that when it lands on this building with an uneven front, it actually looks like it's flat. We can do that to project onto all sorts of objects, and we use it as well now to project onto drone swarms in the sky. Digital electronics is exactly what it sounds. Software engineering, security engineering. We get you started on machine learning in the first year as well. And we get you started on a branch of computer science that's called systems. We start with operating systems. And what systems is about is it is a very complex set of interrelated features where you can't just set one parameter on its own in isolation. You have to configure the whole system to work together as a whole. And if you just change one thing, it might all fall to pieces, doesn't work anymore, becomes insecure, performance becomes terrible. But if you get it all just right, then you have a perfect working system. They're very, very complicated. They involve software, they involve hardware, and it's about doing everything just right. So we'll get you started on that. And we also get you started on the theoretical stream of computer science with some discrete and continuous maths and probability theory. The second year is called Part 1B, and we continue all of those themes. You can see that systems continues, concurrent systems, distributed systems, networks, compilers. These are all very complicated processes that you have to get exactly right. We're doing programming in lots of different languages, and we're doing some of that for machine learning with Prolog, and we're turning that theory away from doing maths on a piece of paper to doing automated reasoning in the computer. It's great if you can prove a little formula on a piece of paper with 10 variables in it, but my CPU has 10 billion variables describing its wiring diagram. You're clearly not going to prove a 10 billion variable example on a piece of paper. And to be honest, you're not going to do it with today's computers either. You need some really clever mathematical abstractions to simplify the problem. And then you need some really clever algorithms that can really bring the cost of computation down to something that's feasible. Otherwise, you end up with an age of the universe style proof. And even if it did, if you ran it in theory, it would finish and would give you the correct answer. It's obviously worthless as a technique if it's going to take the age of the universe to complete. And we start looking at some of those other aspects of economics, law, ethics, the way that computer science fits into society. And alongside all these lectures, and remember supervisions that go with them, in the second year, you do a group project as well, usually groups of 4 or 5 people, and you're actually writing some code. You're building your own little product. You'll have a client, someone who has a need, and you're trying to satisfy their need. You're practicing the requirements solicitation, getting out of them what they want, turning that into a technical design, implementing that, debugging it, and going round a few stages of iteration. Once you've done that, you move on to the third year, and you can specialize in the third year. So you don't have to do all these courses. You choose. Most people choose 7 to 9. That's enough to give them enough choice on the exam papers. And you can see here we've got advanced computer architectures, we've got principles of communication. That's like networking, but on a global scale. These days, we even talk about interplanetary networks. We've already got devices on the moon, in orbit around Mars, even in orbit around Saturn, and they're communicating with us. They are part of the internet. So we really do need to think about these very long latency connections. To Saturn and back is about a fortnight of delay. That's a really long wire. You need some different protocols to make that work. Our compilers have become optimizing compilers. Our algorithms have become advanced algorithms. That means using randomization to search and sample a search space rather than search all of it, so we can find solutions really quickly. We're also looking at quantum algorithms in the quantum computing course. We're looking at bioinformatics. That's a particular category of algorithms, often dynamic programming algorithms that solve problems to do with genome sequencing. Information theory is some background theory that sits behind algorithms and helps you to understand how difficult is the problem that you're solving. Not the solution, but the problem itself. How do you measure how hard a problem is? Well, the answer is information theory, and that tells you whether your algorithm is a good one or a bad one. You can't really say, well, my algorithm takes 10 times or 10 compute units per item in its input. Is that good or bad? Well, it depends what you're trying to do. So information theory will help you understand where good and bad lies. The machine learning, of course, advances to the state of the art, the kinds of techniques that sit behind large language models, but also lots of other forms of Bayesian inference. You might well do one of these individual projects or an exploratory task, a so-called module, on deep neural networks, concurrent neural networks, and what's the other one we offer? Yes, we offer neural networks applied to language processing. So things like the transformer technology that sits behind large language models. And then we've also got some of that important theory: denotational semantics, types, cryptography. Hoare logic and model checking is about the proofs of correctness for our software. Denotational semantics underpins actually almost all software. It's a pure theory course, and it makes you a better programmer. People really don't appreciate at the time how good denotational semantics is. But a year after they graduate, they get back in touch with me and they say, these days when I'm writing my Java code, my JavaScript, my Python, I'm thinking purely about the denotational semantics, the proof of correctness. The coding part is easy. The semantics is helping me to solve this really hard problem. And it's a completely orthogonal way of thinking about your programming. So that's another really exciting part of part two, as we bring the theory and the practice together. If you want to, you can stay on for the fourth year. We do offer an integrated master's course in Cambridge. This is a taught master's. It leads to a Master's of Engineering, an MEng qualification. And you get to do another research project, and you cover some more modules covering the full breadth of computer science. It's also possible to do a master's by research as opposed to a taught master's. That's the MPhil qualification, a slightly higher grade of master's degree, and is good if you want to go into R&D in industry, that's research and development, or you want to go on and do an academic research career. So maybe after everything I've said, you're very keen. So what do you need to get in to do computer science at Cambridge? Well, quite a bit. You need to do some GCSEs. I'm sure you've done those. You need to do A-levels or international baccalaureates or a whole host of international qualifications. Of course, one of the reasons we're doing this session online is because many people are joining us from overseas. And use this QR code if you'd like to find out whether the qualifications that you're taking or that you might take next year are going to be recognized and accepted by Cambridge. That page is on the University Central Admissions website, and it will tell you for each country which qualifications are accepted. What you need to take is mathematics, and if you're doing A-levels, you need to take further mathematics if your school offers it. If your school doesn't offer it, then get in touch with us, and we'll help you. We'll point you at some other resources that you can use to make sure that your maths is up to scratch, even though your school isn't teaching you further maths. You need at least 3 subjects in total, so at least 1 more if you're doing maths and further maths, at least 2 more if you're only able to do maths at your school. Those other 2 or that other 1 subject need to be science subjects. So not things like English literature, but things like physics, chemistry, biology, computer science, electronics, economics does count. That's a very mathematical subject. So you need at least 3. And as I've said on the last line, actually, it's a very competitive course. About 95 to 98% of people with A-levels have got 4 A-star grades in 4 A-level subjects, all taken in their 6th form years at school. We heard earlier on that you need to take the TMUA. So again, there's a lot of information online, so I will run through this bit fairly quickly to make sure I've got time to show you some interview questions at the end. You do need to take the TMUA. If you don't register, we will automatically reject you, and there's no questions asked. Right? You need to take the TMUA. What is it? It's a 2.5-hour exam. It's made of 2 parts, so 75 minutes each, and each part has got 20 multiple choice questions. The first part is about applications of mathematical knowledge. So that's giving you new problems and seeing if you can apply the ideas of maths. So we'll give you maybe 2 circles that intersect and a line that is a tangent to one, and ask you, what is it about the ratio of the radius of one to the radius of the other to the point on the circumference where the tangent touches that makes the tangent go through the exact center of the other circle. And you'd put some equations together and find a constraint. You say, well, if this radius is equal to twice that one, and this angle is equal to a half the sum of them, then it's going to go through the center of the other circle. Something like that. You build your own equations. Mathematical reasoning is about logic, deduction. So I can say to you, the sum of this series of numbers is exactly 100. In this series, all of the numbers are odd numbers, except for 3 of them. Now, of the numbers that aren't odd, 1 of them is equal to the negation of the other one. What can you tell me about these 3 non-odd numbers? And then you might pick from a series of multiple choice answers. There are no calculators for the TMUA test, and also no English language dictionaries. So if you're doing the TMUA with English as your second language, you do need your technical English to be up to scratch. And that's mirroring what the computer science tripos would be like in Cambridge. You submit all your answers to the TMUA into a computer. You will have either scrap paper or a whiteboard where you can do handwritten working to figure out the answer. If you could do these things in your head, you'd be an absolute genius. So you probably will need some pen and paper, and you're given that. There's no pass or fail boundary on the TMUA. You get a score that's based on the number of correct answers you give, and there's no penalty for giving incorrect answers. So it's worth having a guess. Do have a go. And that's, again, it's part of how you learn really quickly in Cambridge, that in a supervision, you will be asked questions, probably by people like me, and you won't know the answer, but you've still got to respond. And that's really good practice for industry, because your boss will ask you questions, your shareholders will ask you questions. Can you do this? And you'll say, maybe. That's not a very good answer. It's, well, yes, we could. This is what it would take. This is how long it will take us. This is what it will cost. This is the extra resources that we would need that we don't have now. Being able to answer and work out the answer on the fly is what you're learning to do there. So start with the TMUA, have a go. To take the TMUA, you do need to register for it. I've got some links coming up for how to do that. Registration will open this year on the 1st of August, and the test will run on the 13th and the 14th of October. You will have to go to a test centre to take this test. It won't be at home. It won't be in your school. You go to an actual test centre, and there will be somebody sort of invigilating that exam. It's a properly invigilated or proctored, you may have heard the term, proctored examination. You'll do that in early October, 13th or 14th. So we will get your results and you will get your results before we decide who to invite to interview. And your TMUA score will be one of the factors that determines whether we invite you to interview. And then the interviews themselves take place in early to mid-December. And then you'll hear in January whether you've got an offer from us at Homerton or us Cambridge, but one of the other colleges, or not this time. There is a cost for taking the TMUA exam. It's £75 in the UK and the Republic of Ireland and £130 in the rest of the world. But please don't let that put you off. For one thing, the opportunity to get into Cambridge is worth a lot more than £75. So if you're in any doubt, just take the exam. If you can't afford £75, it isn't an insignificant sum, there are means-tested bursaries available. That QR code has got all the details. Again, please do apply. I'm one of the people actually that helps to set and run the TMUA test to some extent. And last year we had more money available to give to people who would like a bursary than actually applied for it. So please do apply. We really will help you. Some important points, though, if you would like to apply for a bursary, you do need to do that before you register for the test, because the bursary is like a voucher code. If you're buying something at a supermarket, it's a money off coupon that you use at the checkout, and of course it's a money off coupon for 100% of the cost, so you end up getting your test for free. But obviously you need to have got your code before you go to the checkout to book your test. And you want to apply early. Make sure that there is plenty of space in your local test centre for you on the day that you need to take your test. And if you're applying for a bursary, you may need evidence from your school or your parents to do with the means testing part of it. And it can take time to collect that, especially during the summer holiday when your school is closed, your teachers are on holiday, maybe your parents are on holiday too. The logistics of it, I mentioned you go to a test centre. They're run by a commercial partner of the University of Cambridge, Pearson VUE. These test centres exist all over the world. Within the UK, most people don't need to travel more than 20 miles to get to their nearest test centre, and for a lot of people, it's much less than that. You choose the test centre when you book your test, when you register, and that actually books you a place in the room. You have a chair and a desk and a computer to work on, and that's what you're booking. And these test centres are not only running Cambridge University TMUA tests, they're running all sorts of other tests, in fact, also for engineering, natural sciences, medicine, law at Cambridge, and lots of other university admissions tests, but also lots of other tests as well, like UK driving license tests, immigration tests. All sorts of companies and professions have got professional certifications, and they all go to Pearson VUE test centres. So there are lots of exams running all of the time, and that's why you need to make sure that you get in early and make sure that your nearest test centre has got space for you on the 13th or 14th of October. The TMUA test is quite a secure test. we make it secure because, of course, we want the data to be meaningful. We don't want people to cheat, but also talking to all of our people who have been accepted to Cambridge and the unfortunate people who weren't made offers last year. The one thing that everybody agrees on is that they really were assessed fairly. And that means so much when your whole future could be at stake here, and you're putting in an awful lot of work to prepare your personal statement, to prepare yourself through GCSEs, through A levels, preparation for university. Of course, you want to be assessed fairly, and you don't want anyone to have an unfair advantage over you. So with that in mind, people do understand that we, Pearson VUE, will ask for a photographic ID, passport, driving license, government issued ID card if you're taking this in a different country. If you are using government issued ID, note that it is only acceptable in the country of issue. So, for example, if you have an Indonesian ID card, that will only work if you're taking your test in Indonesia. If you happen to be in the UK at a school here, your Indonesian ID card is not going to be accepted. On arrival, you'll be asked to read and sign the rules. And again, we really mean this. Your entire UCAS application, not just to Cambridge, but to every university, can and will be cancelled if you subsequently break the rules. So that's part of us doing our part to make sure that your admissions process is assessing you fairly and making sure that no one else is given an unfair advantage because somebody perhaps broke the rules and, I don't know, put a photograph of some of the questions on the internet, let's say. Your photo will be taken when you arrive, and video recordings are made during the test. And you're not allowed to take anything into the test centre. So no bags, no food, no bottles of water either. There are some lockers where you can leave anything that you may have brought with you. Give yourself some time. I recommend about 30 minutes to go through all of the security checks when you arrive. So you've got plenty of time and you're not feeling flustered when you start your test. If you do have any special conditions for exams, like 25% extra time, or you have to take in something, perhaps insulin, if you are medically dependent on insulin, then of course you need to take that into the room with you. And of course you can do that for the TMUA as well. But you do need to mention this when you register for your test, and you need to have the appropriate special conditions set up. So again, for example, some test centres, well, every test centre will have some spaces for wheelchair users. You just got to make sure that you register so that you get such a space if that's what you require, and that you register sufficiently in advance that those spaces are still available for you on the day when the TMUA test is being offered. Something I did want to draw your attention to as the test taker is how to prepare for the TMUA. There's a lot of preparation material on the TMUA website. Again, links are coming up. Use the previous year's exam questions and work through them and do that timed. You'll find, unlike probably GCSEs and probably unlike A levels, you're really under time pressure. You have to work really quickly to get through the TMUA in the time that's available. And it takes practice to do that. So, as I've said on the slide, initially it will take you far longer than the time that the exam allows you to answer the TMUA questions. But don't worry, that's okay. When I did my first TMUA exam, I remember I'm setting the wretched thing. It took me ages to answer these questions. But as you practice the style of question, it really, you become much quicker at it, and you'll be surprised at how quickly you get better at it. So don't give up, keep practicing. And if you can't do a particular question, don't give up. Just give up for now. Come back tomorrow and have another go. And you'll find that a little bit of time away from the question and things will start to click. And it's so much better for you to figure out for yourself what the answer is than to ask someone else or to find a solution online. Figure it out for yourself. And you remember that the purpose of practice at anything, musical instruments or the TMUA, purpose of practice is to get better. If you want to learn to play the violin, you don't listen to people playing the violin on YouTube and then think that you can do it, because we all know that you won't be able to play the violin just by hearing someone else do it. You really have to practice, and practice is about doing things, and it's the imprint in your brain that task leaves behind, and that's what learning is. And learning will help you answer future questions. If you just look up the solution, well, you know the answer to that question, but that's pretty useless because you'll never be asked that again in your life. So have a go, time yourself, and come back to questions that you can't do at first attempt. And there is also an online special practice exam that you use in your web browser. It's running the same software as you'll use in the Pearson VUE Test Centre when you take your own real admissions test. So you can familiarize yourself with the software as well. For the practice exam, the software will actually mark your answers live as you're doing it, and it will tell you what you got at the end of the test. And you can go back and look at the ones you got right, the ones you got wrong, and try and figure out why the correct answer is correct. Or you can just see that the one you guessed was wrong. Try again. Ask the software to tell you, give you some feedback on a different answer. So again, that's all really valuable practice, and you can find all of that on the TMUA website. Why would you study computer science at Homerton? Well, we're quite a large college for computer science. We have 6 or 7 computer scientists in each year. Remember, there's 3 years, and some people stay on for the 4th year. So it's quite a lot of computer scientists in the community. But the college is much more than lectures and supervisions. It is that community of people to talk to. And in fact, well, you heard at the start, I direct studies at quite a few colleges. I direct studies at Churchill, Magdalen, Newnham, Lucy Cavendish, Hughes Hall, Homerton, and St Catherine's. And I also arrange all the supervisions for Sydney, Sussex, Murray Edwards, and St Edmunds colleges. So overall, that's about 40 students in each year. It's about a third of the year. And so when we do year group wide events, we're talking about 40 people. That's enough that there's people interested in every different branch of computer science. So by the time you get into your 3rd year and you're thinking about specializing in quantum computing or in optimizing compilers, you already know people who are interested in the same sorts of things. You've been working with them for 2 years by that point already. So you know who to talk to. You've got those that network set up. You can go off and study those topics together and get to be really, really good at them. And that's really important, of course, for computer science. It is a subject where we learn from each other, we discuss things, and new ideas come out of conversation. We've got amongst all these colleges, there are quite a lot of different genders represented, but we've also got Newnham and Murray Edwards there, the single-sex colleges in Cambridge. So, of course, we're naturally going to be a more diverse community than many other subsets of the computer science tripos in Cambridge. There's also a huge amount of experience. Hughes Hall is a mature students' college. Lucy Cavendish is part mature, part normal age. St Edmunds is another mature students' college. So people at those colleges have often been in industry for a year or two. They've got some work experience, and they're bringing that back. That's hugely valuable for people who are coming straight from school. There's huge opportunities here, common interests. We've got enough people to run the weekly technical talks. All of my 2nd year directees of studies give a tech talk in their 2nd year on something they're interested in. Of course, most people do internships between their 1st and 2nd year, or 2nd and 3rd year, and quite often both. So there's lots of stuff going on at Homerton, stuff going on with all of these other colleges we partner with. So it's a good college to choose. What are we looking for in applicants? Well, this is the kind of university standard blurb, if you like, on what we're looking for. Academic ability, potential. Of course, you need to satisfy the entry requirements, but genuine subject interest. You're motivated, you're enthusiastic. And you can demonstrate that through personal projects that you've done. Tell us about that in the 3 parts of your personal statement. We don't care what you've done. What we do care about is, how did you do it? What did you learn from it? What would you change if you're doing it again? Everyone will have different opportunities, different interests. Now, that's great. That's what makes computer science such a broad subject. So there isn't a right thing that you must do. It's that you must have seized the opportunities that you did have, and then recognized what was so good about them, and advanced your interest in the subject in a way that you can tell us about in the personal statement. And that will make you a good fit for the course, and the course a good fit for you, your interests, and what you might like to do. The information that we use to assess applicants is anything and everything that you'd expect. Your academic track record so far, your personal statement, your school teacher's references, your achieved grades at GCSE or age 16 equivalents, your predicted grades for A-level, maybe your achieved grades at A-level if you've taken a gap year and are applying to us with achieved grades. Your TMUA score, of course, we use, and contextualized data. So we're not just looking for big numbers on all of these weird scales. We're thinking, how did you do in your context? What opportunities did you have? Did your school offer further maths, as something I've already mentioned? It wouldn't be fair to compare people who've had different types of education and access to different resources. And contextualizing means we can see you in your context. What opportunities have you had? What have you made of them? And then the interview. So that's the last part of this talk I wanted to take you through. How do you do a successful interview? Well, I suppose the important thing is we're not expecting you to get the right answer straight away. It's a conversation. No one will get the correct answer straight away. You'll have to make some observations, talk to the interviewer, and the interviewer will say, "Oh, yeah, that's an interesting observation. Would that be the same if I changed the question like this?" And you'll respond, and you start to realize why that's such a relevant observation that you've just made. And then the interviewer says, so how does this revelation, how does this new understanding help us solve the question? And you can have another go, and the solution is teased out through that conversation. So really don't expect the answer to just come to you and you'll be able to tell us what it is. And don't try and work in silence, because that's not going to get you the feedback and the interaction with the interviewer that will help you to realize what are the important parts of the problem and the important parts of the solution that you can piece together. Computer science is often about building new things on top of the things we've already got. So we don't want to start again. If you prove something in maths, if you went back to the very beginning, every time you tried to prove something, you'd spend the rest of your life just proving simple things. You have to build up tools and techniques that allow you to take bigger steps through a proof. And you have the idea of a proof by induction. And you know that if you structure your proof in a certain way, you only need to do various little bits. And then you can say, and by the technique of induction, that means I've proved something. And computer science is just the same. We need to build little gadgets, widgets, and plug them together and understand at a macro level, how do they work? Can we understand their behavior, compose their behavior to make bigger things without having to start from the beginning every time? And that's the sort of thing you might expect to get onto towards the end of an interview. So I said I'd show you a sample interview question. Here is a question. We've got a frog and 10 lily pads. And the question seems sort of innocuously simple. At least it's simple to understand. The frog starts at the bottom here, 10 lily pads away from the bank, and it can hop upwards on the diagram. And it can hop either to the lily pad immediately above it, or make a double jump to the one above it. And we want to know how many distinct sequences of single and double jumps will get the frog from its starting position up to the bank at the top. And, well, I'm sure the words of the question make some sense, but how do you go about answering something like that? Well, you might say, if we start on lily pad 10, there are only two things we can do, right? The rules say we can make a single jump or a double jump. So let's try those things and see what happens. If we make a single jump, we'll be on lily pad 9. And if we make a double jump, we'd be on lily pad 8. So I seem to have two options here to get from lily pad 10 to the bank. One option is to go to 9 and then do whatever it takes to get from 9 to the bank. The other option is to go to lily pad 8 and do whatever it takes to get from 8 to the bank. So maybe I can set up an equation here. I can say the number of ways of reaching the bank from lily pad number 10 is the number of ways of doing that from pad 9 plus the number of ways of doing it from pad 8. And with that, well, I've sort of made a useful observation, and maybe my interviewer would ask me, can you formulate that as an equation? Can you think of some variables and then write down something with an equals sign in it, an equation to relate these variables together? So I might scratch my head and say, well, okay, if W is the number of ways of doing this, then what I've just said was W10 is equal to W9 plus W8. And now it's starting to look a little bit more familiar, and I can see that W9 will be W8 plus W7, and W8 will be W7 plus W6, and so on. But where do I start from? Where's the base case? Of course, we're going to need two base cases here, because we're going to have either W1 plus W0 or W2 plus W1. And we're going to scratch our head and think, what does W0 mean? Yeah, I don't know. So our interviewer says, well, is that the only way that you could set this system off? You'd call it bootstrapping. Is that the only way of getting started? And we say, well, okay, we could have 1 and 2, I suppose. And yeah, sure, let's work those out by hand. So there is only one way to get from lily pad 1 to the bank. You just hop straight onto the bank. And there are, in fact, only two ways of getting from lily pad 2 to the bank. So you make one double hop, or you hop to 1 and then hop to the bank. So there's only two options. And now we've got it. We can start off with W1 and W2 and use our formula to work out W3, then W4, 5, 6, 7, 8, and eventually get the value for W10. And now we've got that, our interviewer will think, okay, yeah, this person's good. Let's see what more we can do. Let's change the rules of the game a bit. So here's a new river. It's a narrower river. We've got a top bank and a bottom bank. And our frog is on one of two lily pads. And the rules are changed to say that it can only make single jumps, but it can jump up and down, not always upwards. So we start on the top of these two lily pads, and we've got three questions. What is the probability that the frog reaches the top bank first? What is the probability it reaches the bottom bank first? And is there any probability that it jumps up and down forever without ever reaching either bank? And now, if I were to just pause for a moment and say, what do you think we're talking about here? You'd think some kind of weird logic problem, or maybe you think I'm just genuinely fascinated by frogs and their jumping behavior. Not really. What we're thinking about here is probabilistic algorithms, quantum computers. We want to know, how do you drive down the error rate in a quantum computer? And that's actually the same sort of mathematics as the probability of this frog jumping up and down forever. Is there any probability that our quantum computer won't eventually settle on a solution? So back to our world of little frogs. we can answer this in the same sort of way. So what did we do last time? We came up with some variables. Let's do that again. If we say PT of X is the probability that you reach the top bank first, given that you're currently standing on lily pad X, which is either the top one or the bottom one, then we can write some equations. The probability of reaching the top bank first, given that I'm on the top lily pad now, is, well, if I jump upwards, I'm on the top bank, so I'm done. If I jump downwards, then I will be on the bottom lily pad. And from there, the probability of reaching the top bank first is PT of B. So PT of T is equal to a half, and you're done, plus a half times PT of B. And symmetrically, PT of B is 1/2 PT of T, plus 0 if you jump downwards, because jumping down means you reach the bottom bank first. So there is 0 chance that you reach the top bank first, of course. And now we can solve this, and we get that the probability of reaching the top bank first is 2/3. 2/3 turns out to be quite a magic number. You see that in some complexity theory. There are classes of algorithm that require you to have a 2/3 probability of correctness for what's called acceleration to work. Okay, so that's the probability of reaching the top bank first. We can calculate the probability of reaching the bottom bank first with some ordinary algebra. And what's interesting is that you get 1/3. So we had a 2/3 chance of reaching the top bank first, and a 1/3 chance of reaching the bottom bank first. So what's the probability that our frog jumps up and down forever without reaching either bank? Well, it's 0, right? There isn't any probability left. We've got 2/3 chance of going up, 1/3 chance of going down. That's 1.0 as a sum, so it can't jump forever. This is good news for our quantum computer, because it means it's going to give us a correct answer, or at least it's going to give us an answer. It's not going to loop forever. So we could just spot that. But if we want to do an algebraic method to derive it, then that's perfectly okay in an interview as well. And what you'd get in this case is that PT is 1/4 of PT, and so that's only true when PT is 0. Now, of course, I've rushed through this in a few minutes here for the purpose of this this subject taster session. In an interview, you might have 25 minutes to work through this. So obviously, I've gone through at pace here, but if you were coming up with this yourself, you were making some algebraic mistakes, you were correcting your mistakes, that's all perfectly okay. That's good. Being able to find mistakes in your own logic is a really valuable skill to demonstrate. So really, don't worry if that happens in your interview. What you find is the people who've had a really good interview come out of it thinking, there's no way I'm going to get into Cambridge. That was a complete disaster. And what they actually mean is, although they don't realize it, of course, is I did so well. I got onto that really hard question at the end that only 1 in 10 people will get to. And yeah, that was pretty tough. But that's because I was competing with the really best people who applied to Cambridge that year, the people who are going to be the next year's computer science Tripos first year students. So again, don't worry if it feels like it's difficult. If you do this kind of practice interview, again, don't worry if that feels like it's hard. It's because you're getting on to the end of the question and you are doing well. So I've spoken for quite a long time, and it's time I stopped talking. So I'll open the Q&A session, and I'll stop sharing the screen. I think we've now got Ollie as well. Yes, hello, Ollie. Ollie is one of our second-year students, and is, of course, doing extremely well and enjoying Homerton, aren't you, Ollie?
Of course, yes. Hello. Genuinely.
Superb, superb. And we don't even pay him for this. So there you go. Genuine advice. So how would you like to run the Q&A, Osama?
I'm happy to read out the questions. We've already received four. The first one, I feel like there was a misunderstanding about the open application. The first person thought that if they applied as an open applicant, they have 5 interviews from different parts, different colleges. Whereas, which I want to explain is, if you apply as an open applicant, that means you'll be allocated to a college and then assessed from that college. And first, if you have the requirements and you have the right to TMA score, you'd be invited for interview. And based on that performance, you will either get an offer, get rejected, or get put into the winter pool, which I think is what you will understand as being viewed by different colleges. That's if after interview you don't get an offer from your first college, but you don't get rejected, other colleges will also consider you. But that only happens at the level of the winter pool.
That's right. Yes, it's you wouldn't be interviewed by 5 different colleges or have 5 different interviews. You'd be interviewed by one college.
And the second question was, someone's school said that unless they have a GCSE average of 8, they shouldn't apply because even if they were predicted 3 A stars.
No, no, absolutely not. It's all about context. Maybe if you were at a very well-resourced public school, then having 3 A stars might not be too great in your context, but that's not true for most of us in the UK. Getting 3 A stars is a really good achievement for lots and lots of people, and we really do want those people to apply. Those people go on and do extremely well at Cambridge.
The next question is, does every university require the TMUA? I think I can think of LSE, of Imperial, and other.
That's right. Imperial College certainly does. We partner with them to set the TMUA test. Lots of other universities used it last year. And I think in the coming year, we will see more universities asking for it as well. So if you're thinking of applying to Cambridge, you're probably also thinking of lots of other Russell Group universities. So that means Warwick, Durham, Sheffield, Southampton, and many of those will also ask for the TMUA. So it's not exclusive to Cambridge, no.
The next question is about the test center and to what extent does it matter passing the test center for the TMUA in terms of resources?
No, all the test centers are identically resourced. So in terms of the computer that you're working on, the environment, they're all exactly the same. They will have different numbers of, for example, wheelchair spaces. So if you have special access requirements, then make sure your application is in early so that your local test center will still have the spaces available on the 13th and 14th when these tests are being administered.
The next question is deferring after receiving an offer to be eligible for home key status. I feel like that is a very case-by-case basis because home key is assessed by a specific team, and the regulations around that are always in flux. So unfortunately, we can't answer this very very specific inquiry. You can apply, for example, you can apply for deferred entry. Therefore, your assessment, your fee status assessment wouldn't be assessed on your year of application, but the following year. So if you feel confident about having 3 continuous years of residency that are not, there's a very specific term for that isn't based on you just studying in the UK. You need to be a residual resident. Either way, you feel free to send us this question. I can inquire from the specific team in question and get back to you. But unfortunately, I can't give you it's a very case-by-case inquiry. The next one was, how do we choose colleges in Cambridge? And I feel like both John and Ollie would help.
Yeah, well, maybe Ollie, you'd like to offer some advice as a current student.
Yeah, I mean, you should definitely choose Homerton. No, I think there are a lot of things to take into account. I think Homerton is great food and it's really friendly and it's cheap rent, which are all fantastic factors. And the fact there are 6 or 7 computer science students in the year means it's like you have a sense of community and we have like a Discord group chat where we just like talk about questions or things like all of us have different strengths. And so it's nice to be able to like help each other up. So if you're applying to a college with maybe a smaller cohort, you might want to take that into account. Location matters a lot as well. Homerton is unfortunately quite far away from the computer lab, which forces you to get good at cycling. So it might be a plus. It's not necessarily a downside. But I think there's a lot of different factors. It really depends on who you are. And like for instance, like societies, like I'm part of the music society at Homerton, which is really cool, and like the choir here, which is great. Whereas like if you want to take it more like seriously, like the King's College choir is a lot more prestigious. So it's like random things like that are really case by case.
Yeah, I think in terms of location, it's about 20 minutes cycle from Homerton to the computer laboratory. And if you lived in one of the in-town colleges, it's about 20-minute walk to the computer laboratory. So it doesn't, all the distances within Cambridge. Cambridge is a very small city. So the distances don't really matter. It's just that from Homerton, you'd probably do it by bike. Or the U bus, of course.
Yeah. And yes, there are many buses that uh, U bus one, buses 1 and 7, and there are multiple buses ways of getting. And even if it's close to your department, maybe it's not going to be close to other parts of Cambridge, which you will be frequenting a lot. So again, distance is very relative, and as you said, it is a very small uh, city.
Yeah.
And the next question was about if there was a way to find other interview questions besides the one you use as an example.
Yeah. If you look at, well, actually, the University of Oxford, strangely, has a list of their past interview questions. They're very similar to the styles of interview questions we use in Cambridge. For Homerton and most of my other colleges, all of my other colleges last year, we used an online admissions interview platform that allows us to work on a question together. You can write some code live in the interview and run it and debug it and test it and work on it with us and add new features to it. And by the time we get to the summer and you're thinking about registering for the TMUA, you'll also be able to do last year's admissions interview questions live on that same platform as a practice run for that as well.
Interesting. The next question about what about would you say the course is more theoretical, i.e., CPU networks stuff, or more emphasis on programming and mathematical logic? Yeah,
Yeah, it's certainly a very theoretical course in Cambridge compared to other universities, and that's because we find that that there are some things that are very difficult to learn. Quantum computing, category theory. The way to learn those sorts of things is to talk to somebody else who already understands it, and that's exactly what a lecture is. That's exactly what a supervision is. So we can use the supervision time to get you up to speed with all of these really complicated ideas. And then, of course, software in practice is important too, but you can write your own software to understand things from the lectures. You've got the group project, you've got the individual project, and you'll probably be doing 2 internships as well. We find we don't really need to teach you how to write a Python program because there are plenty of other opportunities to learn that. So we can teach you something in addition, something more valuable than you'd be getting on a software engineering course, for example, rather than a computer science course.
yes. And the next question was about TMUA, the best way to prepare for TMUA paper 2.
Yeah, there are practice papers for both paper 1 and paper 2 on the TMUA website. That's the website is esat-tmua.ac.uk. I'll see if I can put that in the chat so everybody can see that. Or maybe the chat. Will the chat work? Let's see. esat-tmua.ac.uk. So if you can see that in the chat, then that's the link to the website.
I can distribute it around to everyone. I can just share it with everyone. Yes,
Okay, thank you.
no worries. Yes, the next question was about applicants with math and further math, but no third science subject. Would they still be accepted?
Yeah, if you only have 2 maths or science subjects, you won't qualify for entry to Cambridge. You'd need a minimum of 3. And as I said in the talk, 95 to 98% of people are offering 4 A stars, of course, in 4 subjects. So 2 is not enough.
The next question is, what is a good TMUA score for Cambridge?
It's entirely dependent on context, I'm afraid. So the country where you've been taught mathematics, the type of school you've gone to, your age, will all play into how well you ought to be performing compared to your cohort. So it could be anything from 4 out of 9 to 9 out of 9, depending on those factors. That's why we do contextualized admissions, looking at your application holistically, all of the information, all of the metrics together.
Yes. And I think this comment again extends to everything related to admissions. Everything is contextual, and there is no small like minimum value that isn't based on other contextual factors like age, like country, like yes. And again, also based on the cohort of the year. Maybe this year's CMUA is very hard. Shouldn't be discouraged to apply just because it was a very hard paper. Because again, you would be assessed based on the selected cohort or pool of applicants. Can you say that taking A-level computer science would be useful and give you an advantage?
It is useful, yes. An advantage, not particularly. We teach people in Cambridge more computer science between October and Christmas in the first year than the A-level computer science teaches you in 2 years. So that gives you some idea of the pace of Cambridge. And perhaps if you're worried that you don't have a computer science A-level and maybe other people have an advantage over you, just bear in mind that 3 months later that advantage will have worn off. So it's helpful that it introduces you to the mindset, and it gives you some time in your school calendar when you can do some programming. But anybody can do programming at any other time, evenings, weekends, over lunch. There are lots of opportunities to do programming and get stuck into it.
The next question is, are there any GCSE requirements? And there aren't any GCSE requirements. I think at the level of Cambridge overall, there isn't a set requirement grade. But as Dr. Fawcett mentioned, it is seen contextually, but it isn't. If you don't have the right GCSE, you would be disqualified automatically. It would be a factor, but it wouldn't be the thing that's preventing you from having a good application. The next question is, why does Homerton not offer the CSAT?
The CSAT, yes.
The CSAT.
The answer to this is we used to. About 15 years ago, when the CSAT was first introduced, lots of colleges tried it, and its statistical correlation was not really very good. The TMUA is a much better predictor of people's ability to succeed in the computer science tripos and ability to succeed in the computer industry. So we don't need the CSAT. So we don't sort of unnecessarily put people through another exam when the result of it isn't actually very meaningful.
Next question about someone who is not doing 4 A levels, would that be disadvantageous for them?
Not at all. Again, it's all about context.
Yeah.
So if you're doing your 3 science A levels, including maths and further maths, if your school offers it, then please do apply. If you don't apply, you definitely won't get in. If you do apply, then you will probably be invited to interview, and then you'll be able to show us what you can do. And we'd love to hear from you.
I think that extends to the next question, which is about someone who is doing 3 math and 2 sciences, but not further math. And again, it depends on if your school offers it, obviously. And yes, I think the same advice would apply to this one as well.
That's right.
It depends on if your school, at least you would have a chance. If you're doing a math and 2 sciences, you would have a likelihood of being at least with the TMUS good TMUS score. you would be invited to the interview, but then it depends on your performance there as well. You shouldn't limit yourself. Try it and see if you can how well you perform. Can you apply if your school offers further math but you didn't get it due to limited space?
Yes, this is a difficult situation. Ultimately, the answer is yes. Please do highlight on the application form there is a Cambridge specific.
Yes.
Is there anything else you'd like to tell us box?
Yeah.
Tell us in there. I do know that my school offers further maths, and I do know that I didn't take it, but that's because of this reason. And if you can explain that to us, then we really do read these applications. They're not processed by computer. It's not a computer says no problem. An actual human will read it, and we'll be able to take that into account.
There is multiple spaces. There is any other thing you want us to know? There is any other difficulties, teaching difficulties? There are multiple, I think 5 prompts I can think of where you can put that information there and it would be very visible for both during the deselection process but also the interview process. Yeah. Since you are mainly okay. I'm gonna just read this question instead of summarizing it. Since you are mainly taught theory, when do group programming projects? Are you self-learning yourself the code and languages, but applying the theory you've learned? I'm trying to understand this question. So I think there's 2 parts to this. Are you in your slides? You mentioned that group projects happen during year 2.
Year 2, that's correct. Yes. So sometimes people, sometimes people will be using a programming language they're already familiar with. Sometimes they will be picking up a brand new language. See, one of the skills that makes a good computer scientist is when you're thinking about starting a new project and you have to decide which programming language to use, you don't pick one because it sounds trendy or pick one because you've used it before and you already know how to use it. You pick one because it's the right tool for the job. And that means you have to know about programming languages, about the different features, what benefits does each feature bring, what disadvantages does each feature bring, and then make an objective choice about the combination of features you want. And then you pick the language that offers as many of the advantageous features as possible, whatever that language is. And if you don't know it, learn it.
Yes. And I will just speak from personal experience. This year I had to relearn JavaScript to do a couple of data pipelines, and I was trying to do it with Python or with C. And you know what? When you need to use a tool, you will learn it. Reading documentation is not the friendliest process, but you have to make it work. And I think this question is also something Ollie can answer about self-learning coding languages from your experience as a student here.
Yeah, so I think something really good about Cambridge in general is that you learn the sort of thinking methods you can use that abstract away from the actual language you're writing in. So you learn how to think computationally, and so the actual syntax, the language you're using at the end of the day doesn't really matter too much. You can pick it up in a weekend. And so a lot of second-year group projects are done in Java or JavaScript, just because they're sort of the most practical for making applications. But it really is like we learn Java in first year. But there's no JavaScript in the course, but most people know JavaScript because like we pick it up for our own projects and stuff. And so I think you shouldn't really need to worry too much about language. You'll pick it up fine.
Next question is about what areas of math or parts of computer science would you recommend looking into in preparation for CompSci degree?
Probably maths and logic, discrete maths, that's decision maths and probability theory. In terms of the programming side, look into techniques called lexing and parsing. This is to do with compiler design. And it's about understanding that formal languages, not English, not French, but formal languages of computer programs made of keywords that have to fit very specific grammar rules. How can we read in that as a text string and then build a data structure that represents it? It turns out there are lots of ways to do that. And there are some really interesting connections between how grammatically complicated the language is and how long it's going to take to parse it, and even connections to the halting problem and grammars that are ambiguous that you can never parse correctly. So there's a huge amount of computer science that you can expose yourself to by just reading up on lexing and parsing.
The next question is about best ways to prepare for the interview.
Yeah, we have a few resources online. There's some videos. There's actually videos of me, embarrassingly enough, giving mock interviews for various other people. There are also lots of practice interview questions you can find on the web, and work your way through that and explain it to a friend of yours at school, someone doing maths, someone doing computer science, someone doing physics. If you can convince them that what you're saying is true, then you're explaining things in a way that another like-minded scientist is able to understand.
Yeah, that's a good advice. And I think a similar question would be, what advice would you give for personal projects to show passion and knowledge, even though you said broadly that there's multiple ways given the breadth of computer science itself?
That's right. It's really don't try and do every possible thing. Hoping that somehow, if you do something in machine learning and you do some programming and you build a robot and you do this and you do that, you won't have done anything in enough depth there to really show passion and interest. Just pick one, maybe two things, but probably just one. Really dig into that. Get a textbook, do something that's actual hardcore computer science, something you had to find out about, and then understand it, and then implement it, and then look back on what you've done and say, did I do a good job? How do I assess that? If you can explain that to us in the personal statement, you're showing really good computer science skills.
I think also just quickly on that, like choosing personal projects you're actually genuinely interested in, like outside of academics, means you put a lot more time into it, which means you get better results as well. So trying to tie it to some other of your interests means you just get better results, which means it appears better in your application. I think would be
That's
really
a
helpful.
really good point. Yes, thanks, Ollie.
And the next few questions again, I feel like there's a repetition about GCSE and not having good enough GCSE like sixes and sevens, but being predicted good. Again, it is contextual, and
Yeah,
if if you're scoring sixes and sevens, but that's good in terms of your school, you shouldn't worry about the pure value of something. You should think about what is the average in my school, and am I above that at least? So
right.
that's the
And
next
also,
question.
even if you're not, don't worry. Lots of people find that school clicks after age 16. So lots of people really take off in their A-level years and achieve grades much better at A-level than they've ever achieved before.
The next question is about the if you applied as an open applicant, would you get the opportunity for a pool system? Yes, the winter poll is there. If you were selected for interview, but the college couldn't offer you, provide you with an offer, but you were still good enough to get an offer from a different college, you would be put into the pool system, and that would allow other colleges to consider your application. So yes, it's not contingent on you only applying to one college instead of open application. And the next part is, did you mention that water is unavailable during the TMUA exam?
You
Sure.
cannot take in your own drinks bottles into a TMUA exam. That's correct, yes.
Okay. Does the third application reduce your chances of getting into Cambridge?
No, not at all. The everyone who applies is assessed as a cohort, and we're
Mhm.
looking for the sort of cream at the top of that distribution.
Yeah.
It doesn't matter whether you're applying for immediate entry or deferred entry.
And I would say that that's true for all subjects, at least. I've been looking at the data for the past 35 years, and I can say that's true for any subjects, at least for Homerton. I can't speak for the whole university. At least I can speak for us. Could Ollie share any challenges he faced when studying at Cambridge, and also the best part about studying computer science at Cambridge? Go ahead, Ollie.
Sure, yeah. I think probably the biggest challenge is just that there's a large amount of things I want to do. There's a lot of cool things to do in Cambridge, but there is a limited set of things I can choose to do in the time that we have here, just because the workload is high and you cannot load things onto yourself. So you sort of have to choose, like, you can have a great social life and a great sleep schedule, but you'll sacrifice your academics. So you do have to sort of choose in some ways, which I think is the probably biggest challenge. And the best thing, though, I think is just being able to chat to people about like hardcore difficult computer science is like an incredibly rare opportunity. Like back in sixth form, there wasn't anybody really interested in this kind of stuff. And then coming here, it was like, whoa, wait, everybody's interested in this kind of stuff. It's just super cool. Like it just means you can just like grow and just chat to people, make bonds over some really cool stuff.
The next question is about Cambridge and future employment. Whichever wants to answer.
Yes, having a Cambridge degree does make you quite employable. It makes you employable as a computer scientist, as a software engineer, as a data engineer, machine learning scientist, research scientist, applied scientist, and even in related fields, as a patent lawyer, as an example I mentioned earlier. So yes, having a Cambridge degree is very helpful.
More specific questions about supervisions. How are supervisions arranged at Homerton, and does your supervisor change?
Yeah, so I arrange the supervisions. I put all the students into groups. These groups are based on relative interest. People who are interested in the same topic are often supervised together as a group, and people of the same ability level, and also people who think about problems in different ways. So when the supervisor asks a question, one person will answer it. Then the supervisor will invite the second person to give their opinion, and each student will be completely flabbergasted that the other person was thinking about it in such a completely different way, and that's really useful. You're adding strings to your bow, and when you graduate and you're in industry and you're in a meeting and someone asks you for your opinion, you can think, well, this is my opinion, and then you suddenly think, yeah, when I was in that supervision with Ollie, he always thought about it like this, and then you can say what Ollie would say too, and you get that completely different approach. So it does help you to sanity check your own thoughts, to think about whether you've got the complete story, or if you're just perhaps biased by your own preferences, your own experiences.
The next few questions I found at least three that are very similar to each other. About is there any expected prior knowledge about coding and writing code in a specific language for the interview?
No specific knowledge about any programming languages. We don't expect you to know C, Java, Python, or anything else. We do expect you to have some interest in computer science topics. So it might be through programming. It might be through a much more mathematical approach, and doing things like proofs by induction, proofs by contradiction, is setting up a time series of steps that make sense in that order. And that's what imperative programming is. So no, we don't expect any particular computer science knowledge or programming language knowledge, but in the interview, we'll probably expect you to be able to produce a flow chart or a diagram that talks your way through a particular problem.
Again, another couple of questions that repeat themselves about what would you say are useful supercurricular activities, and if, like, anecdotally, only you can mention what are yours or what other people we know in Homerton did, just briefly and anecdotally, of course.
Sure, yeah. I think most people in my cohort at least made sort of games on the side, video games. Most of us were into math to some degree. Like I like did some extracurricular reading, and like I made this little web tool that visualized some math stuff. A couple of us had internships before applying to Cambridge, which is very rare. This is like it's not expected, but sort of things like that that just show you're sort of applying yourself to like seeking out new experiences within computer science, I think is generally what John looks for, I think.
I think, well, yeah, what you mentioned about in the sciences overall, what I noticed is a lot of people do work experience, or even if it's just shadowing, or at least showing that you went ahead and tried to get a perspective of it entails in real life. Although again, it's not required, and it's again going to be seen contextually based on what opportunities were you offered. It's not a hard line on that. Yeah. The next question is about how is Cambridge different from. Sorry, this is already mentioned before. I'm trying to find new questions. I see a lot of questions about combinations, and in general, yes, math ideally further math if the school offers it, and a science at least would be a good combination. So this answers all the questions I see about uh, combinations. The next original question I see is how is computer science taught differently in Homerton, if at all?
Well, everyone goes to the same lectures, regardless of which college they apply to. The collegiate difference is in the supervisions. At Homerton and all the other colleges where I direct studies, you can do any combination of courses in the third year when you're specialising. We do offer all of them. You don't find that you're limited in what you can specialise in later on. And we can find supervisors for all the different courses. So you'll always be talking to someone who knows what they're doing, is an expert in that field. That's of course very valuable. I think one of the biggest advantages of Homerton and also the group of colleges that Homerton is part of is that bigger cohort. Exactly what Ollie was describing, the opportunity to talk to other people, get to know them, get to work with them. And so when you are specialising in the third year, you already know the right people to talk to.
And another question that you might have addressed, but again, question about comparison of computer science at Cambridge overall, as opposed to other UK universities. You mentioned it being a bit more theoretical and not focusing solely on languages. I feel like I'm already answering the question. And
That's right. That is the answer to the question. We use the lecture and supervision time to cover a lot of theoretical computer science because we know people are capable of applying it themselves. They don't need to be taught how to type on a keyboard, for example. They can already do that. And well, software engineering, you can learn a lot of that on an internship.
the other question is about how are AS seen? If a person is taking 3 A levels and an AS or 2.
It can give some useful experience, but I don't think we would make an admissions offer based on an AS subject.
I haven't seen that ever. Yeah.
No.
A question for Ollie about study spaces available at Cambridge and Homerton as a computer science.
Yeah, there's a ton. There's a lot of them. The library at Homerton is really good. It's open 24/7, which is particularly good for computer science students because our sleep schedules are not ideal. It's fine to study in your room as well. And like it's quite easy to go to like there's a Costa down the road. And like if you do want to go to the computer lab, it's as John said, only 20-minute cycle away. And that's also basically 24/7. So you can go late at night with your friends and be in the lab, which is a good experience to be with other computer science people. But yeah, there's a ton of places to study as hopefully you'd expect from Cambridge.
And in terms of, for you again, in terms of workload, can you describe more on the amount of supervisions, lectures, your weekly workload, perhaps?
Sure.
Yeah.
Yeah. I think it is a high workload, but insofar as a normal job is also a high workload, I think. Like before uni, I was working full time at a startup, and I found that significantly like I'd say more work than Cambridge. That was a proper like 9 till 6 every day. Cambridge, if you treat it like a 9 till 6, will be very easy for you, I think. But the problem with being at university in general is like it's not really a 9 to 6. You want to go off and go like do things in the evenings or like random events or like at 11 a.m. Like it's not standard like that. I think the workload is probably about equal to or less so than a full-time job. But also again, you can throw a lot more hours into it if you want to get a really good mark. You can throw a lot less hours into it if you want to focus more on having fun. But it is sort of self-directed.
Going back to something that was mentioned about the website for interview questions. Was that about the Oxford website, I believe?
That's right. Yes, just do a Google search for the University of Oxford Computer Science admissions interview questions, and you'll immediately turn up a whole list.
Yes, I will just type that for the person and send it to them. Okay. And more questions about TMEA. Can you send the 2 papers together?
Yes, the 2 papers are taken back to back. It's in a 2-hour 30 block.
Is that extra activities section? I'm not sure the activity section on the UCAS form. Um, what I'm not sure I agree with what is seen is there is my Cambridge application, and that has prompts where you can describe more. I think what we pull from UCAS is a table of your work experience or any that is pulled, but I would recommend if even if you mention it on the UCAS application, just re-mention it again on the My Coverage application, just so you're sure that whatever information on extracurriculars appears there as well.
Yeah, I think that's referring to the personal statement. It used to be one large text box and is now divided into 3 small pieces.
Oh, okay, that makes sense.
But yes, that certain information certainly does come through to us. We do read it, and the sorts of things to tell us are about these unique opportunities. Personal means something that's happened to you that might well never happen to anybody else ever again. It's a unique set of opportunities that you've benefited from. What did you do? How did you take them up? What did you learn from it?
Interview question: would you discuss the personal projects mentioned in application during the interview?
Not usually. If there's something unclear that we wanted to explore, we might spend a minute or two talking about it. But really, in interview, we want to have the same problem discussed with everybody, so that we get a single metric that's comparable across everybody we've seen. We don't want to be having 120 different conversations and then try to put people into a rank ordering. We want our process to be much more rigorous and fair.
A question about interviews. Interviews again are arranged at the level of the college that is assessing the application. Some colleges do it in person, some online. For us, for Homerton, for next year, for computer science, it will be online. And yes, there is a online whiteboard. And if you're having difficulty with the online whiteboard, uh, well, again, I think John would have more.
Yeah, that's right. I mean, there certainly is a whiteboard. If you would like to draw as a diagram, you're very welcome to do that. Other people will draw with a pen and paper and then just point the webcam at the pen and paper and show us the diagram that way. In practice, almost everybody shares what they're doing in the form of code. So it's just ASCII text. You're typing into a web page. We're looking at the same web page. Everything you type, we can see. Everything we type, you can see. So it's a live coding environment where we're both sharing the same source code.
And that was the last 3 questions for now. I just need to close it at some point. So I think 3 questions is: Is there a CS degree with a year in industry at Cambridge?
No, we don't do a sandwich course in Cambridge. People could do that year in industry as a gap year before coming to Cambridge, or of course do it as their first year of employment after Cambridge.
Any memorable instances from during interviews of anything that candidates said that was, although even if it was exceptional then, I don't think it would be exceptional now, to be honest. But essentially, yeah, you can just talk about in general what's any indicators of good performance, although you already mentioned the key ones.
That's right. Every year, of course, we come up with new interview questions, and of course, we test them as a collection of academics. We'll interview each other, and what we're really interested in is what are the different ways that people try to tackle the same problem. And part of that process is to improve our interview questions. So by the time we ask you these questions, they're very clear, and we've eliminated any misunderstandings that tripped up each other, our colleagues, as we test these questions on each other. But of course, as soon as you put questions in front of candidates, somebody comes up with an insanely complicated or really clever way of doing it, and you just think, "Oh wow, this is a brand new way of solving the problem," and it's brilliant. And then we're thinking live on the spot as well. Everyone does something a little bit different. They're really interesting conversations.
I think the next question means is like, to what extent is for a good extracurricular project, for example, is it about complexity or is it about what is the good indicator? Is it about how useful it is, how creative, how complex?
All of the above. It very much depends on what you would like to get across to us as the thing that you benefited from. So if, for example, this is the most complicated algorithm you've ever done, that's a really good thing to tell us about. That's really important. If you are trying to build something that's algorithmically really simple, but it's to help your next door neighbor who is perhaps using a walking stick and they find it difficult to operate a mobile phone, and you've invented something that helps them, then how did you collect the data? How did you test it? How are you? What evidence have you got that you've improved your neighbor's life? That could be the story you want to tell us. So it can be anything and everything to do with computer science, your opportunity, what you've done, how you did it.
The same person extended it in, for example, if someone is making a video game, they focus on the algorithmic side, showing skill in computer science, or the user experience side.
They're both parts of computer science. The user experience side is for how much do people enjoy it? How often do people get frustrated by it? Maybe even if you offered this video game in your local cinema, how much would people pay to play this game while they're waiting for their film to start? If you're thinking about the algorithm side, then how do you make a computer opponent for a video game that has a programmable level of difficulty? If you have an AI opponent that's incredibly good at the game, then no one will play your game more than once or twice because they'll keep losing, and because the AI is just so good. So how do you make a kind of stupid AI that gets cleverer as the human is learning the game and getting better at it themselves, so that the AI is constantly offering a challenge, but a challenge at the right level? That's actually really hard to do. If you've come up with a way of doing it, and you can tell us about that, that would be really interesting to hear.
That's a wide range of questions, I feel like. If there is anything in your remaining notes, Ollie or Dr. Fawcett, if you want to share them, please feel free. Otherwise, I feel like we can wrap up things. Have any last words?
Okay, nothing else from me. Thank you. Thank you, everyone, for coming along. Sorry we overran a little bit. There were lots of really good questions there. Please do apply. Good luck.
Sounds good. Thank you, everyone, for joining us. Ollie, do you have anything to say?
No, it's good. Best of luck.
So yes, thank you everyone for joining us today. The recording will be uploaded on the YouTube channel I sent in the chat. And yes, have a good evening, everyone. Bye.